Hello, welcome to video 1, section 4.3, linearly independent sets and bases. So as before, a set of vectors v1, v2 up through vp in a vector space V is linearly independent if this equation, c1 v1 plus c2 v2 up through cp vp is equal to 0, has only the trivial solution where all of the scalars are equal to 0. Okay, so the only thing that's changed here is that we're looking at vectors in a vector space V now instead of Rn. And we have this analogous theorem from theorem 1.7 here that says a set of vectors in a vector space V is linearly dependent exactly when one of them, some Vj, is a linear combination of the others. Okay, so let's do a quick example here. If we've got P1 is 10, P2 is x squared, P3 is 3x squared minus 5. These are all vectors in P2, really polynomials of degree 2 or less. We want to show they're linearly dependent, and the quickest way to do this is to observe that P3 is a linear combination of P1 and P2. So we can see that P3 is just equal to exactly what? 3P2 minus a half P1. So by theorem 4.5, 4.4, the set P1, P2, P3 is linearly dependent. And you might rightly ask, why didn't I put the argument P1 of x, P2 of x, P3 of x? We'll be a little bit, oops. Yeah, you can call the function by its name or include the argument. Either is okay, I think. Sure. So let's get to the definition of basis here. So let's let H be a subspace of a vector space V, an ordered set of vectors. So the order is important. And this R here doesn't look right. Let's do this again. An ordered set of vectors B, so B1, B2 up through BP in our vector space V is a basis of H if two things happen. One, we want B to be a linearly independent set. Linearly independent set of vectors. And then two, we want the script B to be equal to the sorry, I got this backwards, didn't I? We want H to be equal to the span of the vectors in B. And how we can think about this is that our set B is large enough to span all of H, but doesn't include so many vectors that we get linear dependence. So it's sort of some kind of balance of big enough but not too big. I mean, we'll see eventually is that this is really what we're getting in a basis is a really efficient spanning set. Yeah, so let's see some examples. Sure, if we take E1 to be the vector with a 1 in its first slot and zeros elsewhere, E2 to be the vector with a 1 in its second slot and zeros elsewhere, and En to be a 1 in the nth slot and zeros elsewhere. All of these vectors, these columns of our identity matrix, they form a basis of Rn. Yeah, E1, E2, up through En forms the basis. Oops. Basis of Rn. And the invertible matrix theorem sort of helps us see why this should be a basis. It's going to tell us that since these vectors span Rn, and there's n of them, then IMT says they're also linearly independent. Oh, and I'm sitting on my key. Hold on a second. Oh, so much better. You ever notice something is wrong, you can't quite place what it is? That was it for me. Okay. This is called the standard basis of Rn. Standard basis. Okay. Pn as always is the set of polynomials of degree less than or equal to n. This also has a standard basis. 1x x squared up to x to the n, say basis for Pn. Yeah, also call it standard basis. Standard basis. Okay, and we can see showing linear independence is sort of a deepish theorem of algebra. Showing that it spans is pretty quick. We can at least see why it spans immediately. If P of x is in this vector space, then by definition, P of x looks like a naught plus a1x plus a2x squared, all the way up to a n x to the n. So we can see, oh sure, this really is a linear combination of the basis vectors in our set of vectors. So we see that P of x is in the span of this set. So we won't show that it's linearly independent yet, but it's a fact from algebra that we'll see eventually. Okay. Pardon me while I fuss over the little n here. Let's do another example. You might ask, do the vectors v1, v2, v3 form a basis of R3? And you might stop me and say, wait, David, we already have a basis of R3. What is wrong with E1, E2, and E3? And there's nothing wrong with them. It's just that it'll be to our advantage later on to be able to pick a basis, any basis, some specific basis for whichever vector space we're interested in. And so it'll be very helpful to be able to say, yeah, to choose. So yeah, some bases will be more convenient than others. So we do want to consider, do these vectors form a basis of R3? And to answer this question, we'll do something that we've often done in this class. We've stared at it and tried to think, well, how can I make this into a linear system that I can solve? Because that's the strong computational aspect of this class. It's just, yeah, it's just row reducing matrices basically. And so another way of asking this question is, so does C1 V1 plus C2 V2 plus C3 V3 equals 0 have a non-trivial solution? Right? If it does, then our vectors are linearly dependent and it can't be a basis. If it only has the trivial solution, then we've got three vectors in R3 that are linearly independent. And from our invertible matrix theorem, we'll get that actually they span too. So this question completely answers the problem. So all we need to do is to find non-trivial solutions to this equation. That sounds an awful lot like what? We want to row reduce. We'll row reduce the matrix. 1, 2, 3, 2, -1, 4, 0, 5, 2, 0, 0, 0. If you didn't want to include this augmented column of zeros, I would absolutely forgive you. But for the sake of making a choice, let's row reduce this matrix. And actually, I think you've seen me row reduce lots of matrices. Maybe I'll skip this one for the sake of time, since these videos are a little bit long this week. Okay, so then this is going to row reduce to 1, 0, 2, 0, 0, 1, -1, 0, 0, 0, 0, 0. Okay, so we're getting that what? That our third variable x3 is free, which means we have infinitely many solutions. Oh, there's an alarm going off on my phone. Infinitely many solutions. So not just the trivial solution, but others. And if we have more than just the trivial solution, well, it's done now. If we have more than just the trivial solution, then means we have a non-trivial solution. There is a non-trivial solution. Or the other option would be if we had 1, 1, 1, and something over here. Or sorry, if you have 1, 1, 1 and all zeros here, and that would say, okay, there's exactly one solution. It's a solution where x1, x2, and x3 are all 0. That's a trivial solution. This is saying no. For every value of x3, we can produce a solution for this equation. Okay, so there's a non-trivial solution, which means our vectors are linearly dependent. And so they do not form a basis. Of R3. Boom. Sorted out. Yeah, okay. So then the next thing we might want to talk about is, okay, in this problem, can we show that the span of the first three vectors is actually equal to the span of the first two? Right? If they weren't a basis, if they're linearly dependent, how can we show the spans are actually equal? Okay. All right. So let's notice. Notice what? X1 is equal to what? Here we've got x1 plus 2x3 is equal to 0, so x1 is equal to -2 x3. X2 minus x3 is 0, so x2 is equal to x3, and x3 is free. So what I would like from this information is an example equation that says, okay, so many v1s plus so many v2s plus so many v3s is equal to 0. And that'll help us express v3 as a linear combination of v1 and v2. And that, I think, is going to be key to showing that actually these two spans are equal. So if x3 is equal to 1, and here it could be any number you like, but 1 is convenient for me, then what? Then x1 is equal to -2, and x2 is equal to 1. And so we get that, what? Minus 2v1 plus v2 plus v3 is equal to the 0 vector. And if you don't believe me, I encourage you to go back to v1, v2, v3 and check twice this. Sorry, minus 2 times v1 plus v2 plus v3 is equal to 0. Certainly checks out in the first line. Here we get -4 minus 1 is equal to 5. Okay, that checks out. -6 plus 4 plus 2 is equal to, okay, I think it works. Okay. So we want, what do we want? We want the span of v1 and v2 to be actually everything here. So really we should express v3 in terms of the other two. I think that'll make our life easiest. So this means that v3 is equal to 2v1 minus v2. So yeah, if u is a vector in the span of v1, v2 to v3, then all we can say for sure is that u is some combination, I don't know, a1 v1 plus a2 v2 plus a3 v3. What we'd like is actually u to be some combination of just v1 and v2. And what we're going to do is just replace v3 by 2v1 minus v2. This is a1 v1 plus a2 v2 plus a3, and now we've got 2v1 minus v2. So now if we're collecting everything in front of a v1, this is really 2a3 plus a1 v1 plus what? a2 minus 1 v2. All right, this time. Boom. Okay. A2. Oh, sorry. Yeah, not -1, but minus a3. And that's everything in front of a v2, right? Minus a3. Okay. So this is so u is in the span of a v1, v2. Okay. And then it's clear. Also, we also have that the span of v1, v2 is in the span of v1, v2, v3. Okay, so that shows that these two spans are actually equal. And the reason I wanted to, one of the reasons I wanted to mention this was as a intro to this little theorem we have, theorem 4.5, which says if you have a set of vectors S such that, we take H to be the span of this set, then two things, there's two considerations we want to make. If we've got some VK, one of our vectors VK, that is a linear combination of the other vectors in S, then if we take S and pull out VK, that new set still spans all of H. So there's no way that we go from spanning with a if we remove a vector that's a linear combination of the others, it doesn't change the spanning set. Sorry, this is written incorrectly. If H is non-zero, if H is not the zero subset, then so as soon as we have a spanning set, some subset of these vectors actually is a basis for H. So roughly what it means is that if you start with some spanning set, you can throw away linear combinations of vectors until you get down to a basis. Yeah, if your spanning set is too big to be a basis, i.e. there is some linear dependence, that means that there's some vector is a linear combination of the others. Then you can toss it out and toss it out and toss it out until what you get down to still spans and now is also linearly independent. Okay, and that was what we were supposed to be seeing, or that we did sort of an example of this here, where now we could check. Yeah, you could check that v1 and v2 actually are a basis for the span of v1 and v2 now in R3. Okay, I think that's everything I had planned for this first video. I'll see you all in a sec with video number 2. Take care, everybody.